universe engages us with both its unending vastness and its rich diversity. The farther we look, the more we discover, and the more we realize how much there is yet to understand about the cosmos that surrounds us. The challenge for astronomers is that our view only extends so far. Our technology allows us access to a finite part of an infinite reality. Physically, we are bound to the Earth and the nearby worlds of our solar system. With our observatories, we can only see the light that happens to come our way from the stars and galaxies. How then can we hope to explore the parts of the universe we can't reach and can't see? Fortunately, there is a way. One that doesn't just enhance our senses, but enhances our ability to imagine the universe in a virtual way. Once there was only one way to explore the distant universe, through the eyepiece of a telescope. But times have changed. Astronomers can now turn to their supercomputers to conjure up representations and simulations of what goes on in reality in order to see and understand reality better. Along the way, they've created something that's close to a new kind of art, the art of cosmic visualization. As a starting point, computers can help transport us to where we can have a new and better vantage point on places we've already explored. One such place is the moon. Humans have not set foot on its desolate surface since 1972. Since then, many robotic spacecraft have orbited our satellite, taking countless images and sending back a torrent of topographic and mineral data. Most recently, scientists have obtained some of their best views of the moon with NASA's Lunar Reconnaissance Orbiter, LRO for short. LRO carries a powerful camera as well as an altimeter, which bounces laser light off the moon's surface and measures the time it takes to reflect back to the spacecraft. Together, this information can be assembled in a computer to provide a three-dimensional perspective of lunar craters and mountains, bringing us much closer to the surface than the spacecraft actually traveled. What is most astonishing about this particular flyover is that although it looks very realistic, no astronaut has ever seen this part of the moon. And scientists are interested in finding out more. These views are not simply aesthetic choices. They are created to help planetary scientists better understand the complex history of the moon's ancient surface and identify future landing sites where rovers or astronauts may one day unearth a deeper understanding of our nearest neighbor in space. After the moon, humanity's next step into the great beyond could well be Mars. No planet apart from our own has been the subject of such intense scrutiny and the destination of so many robotic missions. In recent years, it seems an entire fleet of spacecraft has descended on Mars, either roving over its terrain or imaging its surface from orbit. Like its lunar counterpart, the Mars Reconnaissance Orbiter studies the planet from high above. But this computer-simulated flyover, created with data from the spacecraft, makes it feel like we're staring out of the window of a Martian airplane. Traveling to Mars would present the biggest challenge humans have yet faced in space, and it is still far from routine for the robots blazing a trail here. Lots of data is key to planning an effective exploration. Even for an unmanned rover, it is crucial for researchers to know what is waiting for their vehicle before it sets down on the planet's surface. Here, information from Mars Reconnaissance Orbiter has been turned into an in-depth tour of Gale Crater, now selected as the landing site for Curiosity, the next rover to be sent to Mars. The crater reveals an intriguing landscape. Sections of its floor are covered with ancient sediments that may have been deposited long ago by flowing water. At the center of the crater is a towering mountain, 5 kilometers high. How it came to be there is unknown, but its layers of rock were laid down at a time when Mars may have been warm and wet enough to support life. Researchers hope views like this will help them chart an optimal surface route for Curiosity's challenging mission. In a completely different way, astronomers have used computers to obtain a three-dimensional view of the Orion Nebula, one of the nearest and most spectacular star-forming regions in our galaxy. Here, the computer allows us to travel many times faster than the speed of light, flying around the cluster of bright stars at the heart of the nebula. These stars illuminate the hydrogen and other gases within the nebula, making them glow. They also drive back the gas with a strong stellar wind, which creates a hollow space inside the nebula and exposes the embryos of new solar systems in the midst of formation. Such views are both artistic and scientifically accurate, but they merely scratch the surface. The real power of computers involves not just exploring new landscapes, but in revealing the hidden forces at work in shaping our universe. The roots of astronomy lie in our attempts to keep time. Haitian skywatchers once used the stars to divide the night. They tracked the sun's yearly trip through the stars by watching the constellations appearing out of the sunset and fading into the dawn. Now, the arrival of powerful computers is allowing astronomers to deal with time in a new way. The real power of supercomputers in astronomy is not simply to show us what the universe might look like in places that are too hard for us to get to. It's to show us how things change over vast timescales that we could barely comprehend, let alone experience. In that way, a computer can be like a cosmic clock. Just set it running and see what kind of solar system or galaxy or universe takes shape. Astronomers have long thought our solar system formed out of a disk of debris that swirled around the newborn sun 4.5 billion years ago. When we peer with telescopes at star-forming regions elsewhere in our galaxy, we can find evidence of disks around other young stars. But how exactly did it happen here? And how did it lead to the family of planets we recognize as our solar system, including one planet, Earth, that ended up in just the right place to support life? Because we can't go back in time to see how we got here, astronomers use the information gleaned from observing other stars to set up computer simulations of our solar system's formation. Such simulations offer a virtual laboratory to test detailed theories of what really happened. Astronomers have had some success modeling solar systems, but can we turn the clock back even farther to simulate the birth of galaxies? According to current theories, the galaxies we see today formed from smaller galaxies, created when the first stars died and left behind black holes that act like cosmic glue. The black holes came together, creating cores around which larger galaxies formed. As we see, galaxies did not form in isolation. Often, many formed in the same part of space, gathered in clusters and superclusters. In some cases, two galaxies may run into each other. This can be a gentle collision, a cosmic fender bender in which the vast distances between the stars in each galaxy means they pass right through each other, distorting only slightly due to their mutual attraction. In other instances, simulations show how celestial fireworks can occur, with galaxies smashing into each other, exploding, and recreating in a completely new form. As we look around the sky, we see many examples of interacting galaxies. And now, supercomputers are helping us turn time backwards to see how they got that way. Even our nearest galactic neighbors are in the process of interacting. The Andromeda Galaxy is 2.3 million light-years away. Through a telescope, it's also possible to see a smaller companion galaxy. Modeled here, with each star represented as a point, we see the two galaxies engage in a long, slow, gravitational waltz. According to this simulation, the dance leaves a big impression on both galaxies. But, as is usually the case, it is the smaller partner that is more obviously affected by the gravity of its larger neighbor. Our own Milky Way is smaller than Andromeda, and observations reveal that we are also on a collision course with this galactic monster. Flashing forward billions of years into the future, we see the fate of our own galaxy is to collide and ultimately to merge with Andromeda. Will this affect our planet? It's hard to imagine that it will not. By then, Earth will be into its old age and very likely no longer a habitable world for humans or anything like us. But here, with the help of a computer, we can see how the future will play out far beyond the boundaries of our own experience. After centuries of scanning the skies with telescopes and decades of sending unmanned probes to other planets, we should know our own solar system pretty well. But we can't see everything. For example, we know the formation of our solar system should have spawned a zone of small icy bodies well beyond the orbit of Neptune. Pluto, discovered in 1929, may simply be one of the largest members of this group, collectively known as the Kuiper Belt. Since 1992, many dozens of Kuiper Belt objects have been discovered, and estimates suggest there could be up to 70,000 more. Now, a computer simulation can help show us how the Kuiper Belt may appear to an infrared telescope observing our solar system from a distance. It appears as a glowing ring because collisions within the belt create dust which radiates a faint infrared light. A gap in the ring reveals the presence of a planet. In this case, Neptune. Scientists can also take the simulation backward in time to see how the Kuiper Belt is likely to have changed over billions of years. Eventually, it devolves back to a simple ring, exactly what's been found surrounding some other stars that are much younger than our Sun. The computer is our gateway to understanding the hidden influences at work in the cosmos. The ultimate hidden influence is the influence of dark matter. Discovered through its gravitational pull on stars and galaxies, dark matter gives off no light and is not directly observable by any other means. A lump of dark matter would pass through Earth like a ghost, since it does not interact with ordinary matter at all. Yet the dark matter in our universe outweighs normal matter by 5 to 6 times, and its gravitational pull has had a profound effect on the way the universe has evolved. Using computer simulations, we can now imagine what it would be like to fly through our own galaxy and experience it as though we were wearing dark matter glasses. The effect is something like driving through a snowstorm, but on a galactic scale. In this visualization, everything made of atoms, including stars and planets, have been rendered invisible. What we see is only dark matter, which the computer shows us forms in countless clumps that orbit around the galaxy's center. Over the course of our solar system's history, Earth may have flown through many of these clumps, but we would never know this. However, the presence of this dark matter guides how the stars move and shapes our galaxy. The effects of dark matter grow even more significant as we look to larger scales. For example, when we peer out to the universe over hundreds of millions of light years, we find the galaxies are not distributed randomly. Instead, we find there is a pattern to the way the galaxies are organized. Astronomers call it the cosmic web. Matter has tended to concentrate, and galaxies have tended to form in sheets and filaments, leaving surrounding voids or bubbles where matter is relatively scarce. What is the source of this cosmic web? With the help of supercomputers, astronomers have been able to determine the answer. When dark matter is added to the equations that show how the early universe took shape under the influence of gravity, it is the cosmic web that emerges. There's no question that the use of supercomputers has both broadened and deepened our knowledge of how the universe works, and that computer simulations have allowed us to travel through time and space in a virtual way so that our minds can go where our bodies cannot follow. The best part is this is just the beginning. Supercomputers are only getting faster and better, and that means the virtual universe that's opening up before our eyes is probably going to be even more imaginative and spectacular. Perhaps there's an even deeper insight we can glean from the new power of computers and the way they are being used to help us understand nature at the largest scale. What these simulations tell us is that the cosmos is inherently mathematical in nature. Whatever our universe is, and however it came to exist, it is governed by numbers and relationships that can be represented in a computer. The universe is not getting smaller or easier to understand, but with computers to aid us in our future explorations, we know that much, much more of it will now be within our grasp.